Hi everyone, here are your section 2.3 notes. We're going to be getting into complex zeros. So let's go ahead and start with the fundamental theorem of algebra. The fundamental theorem of algebra says that a polynomial of function x with degree n will have n number of complex zeros, or real and non-real. So whatever your degree is, you are going to have some type of combination of real and or non-real zeros. So some of these zeros may be repeated, which is what we talked about last class with multiplicity. The linear factorization theorem says if f of x is a polynomial function with your n is greater than 0, then f of x has precisely n linear factors. Okay, so if we have something to the fourth degree, then we should be able to write out 4 linear factors. If we have something to the third degree, we should be able to write out 3 linear factors. So our fundamental polynomial connections, I guess I should scroll this up so I can get all 3, says if f of x is a polynomial, the following statements about a polynomial function f are equivalent if k is a complex number. So if x is equal to k, will be a solution. So is a solution, or also known as a root, or also known as a zero, of f of x when your output, your range, your y is 0. K is a zero of function f if the above is true. And then x minus k would be a factor. So is a factor of f of x. Okay, which we probably already kind of knew this stuff. But so now all we're going to be getting into is, well, what happens when we don't have nice zeros? So what if we have radical zeros, or what if we have imaginary zeros, right? So this gets us into the conjugate root theorem. So remember back when we were simplifying and verifying trig functions, the conjugate of 1 minus sine of x was 1 plus sine of x. The same thing applies when we're talking about complex numbers. So if p of x is a polynomial with rational coefficients, then the irrational roots of p of x equals 0 occur in conjugate pairs. So irrational roots will always be in pairs. So that is when you have something like a plus the square root of b as a root, then its conjugate of a minus the square root of b would also be a root. And same thing for imaginary. So if we have something like a plus b times I, remember I is our imaginary number, is a 0 of a function, then the conjugate of a minus bi would also be a 0. And we need to remember this when we're talking about finding polynomial equations. So here in example 1, it says, find a cubic polynomial equation with the roots of x equals the square root of 2 and x equals 5. So we know that it needs to be cubic, which means that I should have 3 linear factors, but I only have 2 zeros. But that's okay, because if x equals the square root of 2 is a 0, then its conjugate of minus 2 would also be a 0. So now let's turn those into linear factors. So positive square root of 2 would have a linear factor of x minus the square root of 2. Negative square root of 2 would have a linear factor of x plus the square root of 2, right? Because wouldn't a positive square root of 2 make that 0? And wouldn't a negative square root of 2 make that 0? Yes. So those are my 2 of the 3, and then my third one's going to come from that positive 5, which would be x minus 5. Okay, and it's saying leave it in factored form, so we can just stop there. If I needed to put it into standard form, then we would multiply it all out. Okay, so let's go ahead and do that in example 2. So write the polynomial function in standard form and identify the zeros of the function and the x-intercepts of its graph. So we have the function f of x is equal to x plus 2. So there's one of my zeros. And then I must have 2 imaginary zeros. at plus or minus I root 3. So now let's see if we remember how to multiply imaginary numbers. Let's start there first. Always start with that one. So when I FOIL that out, I get x times x, which is x squared. Here I'm going to get my two middle terms. Does everybody see how they're going to cancel out right away? So I'm only, well, I guess I'll write it out just so you have it in case you don't remember. So those are going to cancel out because I have a difference of squares. So then I only really care about the first and the last. Now let's pay attention to when we multiply that last. I have a negative I root 3 being multiplied by a positive I root 3. Well, that's the same as taking a negative I times an I times a root 3 times a root 3. I'm just reordering my parts of the products. So negative I times I would be negative I squared. Now, do you guys remember what I squared is equal to? So I squared is equal to negative 1. If you don't remember that, you're going to want to make a quick star somewhere on your notes so that you remember that. So if I squared is negative 1, then the negative of I squared would be positive 1. And root 3 times root 3 would just be 3. So that whole entire, this multiplying right here, just becomes a plus 3. So when I multiply those last two together, I get x squared plus 3. And then I have my x plus 2. So now let's multiply that out. So x to the third plus 2x squared plus 3x plus 6. So f of x is equal to that. Okay, my zeros, we can go back to the factored form. I have zeros at negative 2. I have 0 at I root 3 and negative I root 3. And then we have a y-intercept at, if I plug in 0 for everything into, let's say the final one, everything will go away except the 6. So 0, 6. You can write your x-intercepts as x equals negative 2, x equals plus or minus I root 3 too. I would accept that for an answer over set notation. That's up to you. Okay. So now let's move on to the next page. So finding a polynomial given complex zeros. So we can write a polynomial function of minimum degree in standard form with real coefficients whose zeros include the following. So I have a 0 of negative 3. So that means I'm going to have an x plus a 3. A 0 of negative 4, which means I'm going to have an x plus a 4 as a linear factor. Now here I have an imaginary 0 of 2 minus I. So now we got to think about what that would look like. Well, if that would be a positive, wouldn't that turn into x minus 2 minus I, right? Because I would put this in place of here, and it's always minus to start out with, unless it's a negative, then it goes to a plus. So really that turns into x minus 2 plus I, right? Everybody follow that? But now I need to do the conjugate of this, because remember, for our imaginaries, we always have a conjugate of it. So the conjugate of 2 minus I would be negative 2 minus I, which would turn this into an x plus my 2 minus I, which would go to x plus 2 minus I. Oops, my minus is turning into a, there we go. All right, so we have an x plus a 2 minus I, and we have an x minus a 2 plus an I. Okay, everybody needs to stop. Freeze. I just realized that I did something wrong. Hopefully you noticed it. I didn't do my conjugate right, did I? I did not. All right, so I'm going to redo this conjugate imaginary start. Sorry if you were doing this in pen. So what's the conjugate of 2 minus I? Not negative of it. Wouldn't it be 2 plus I? That would be the conjugate. So my two linear factors would be x minus my 2 minus I, which that one was fine, x minus 2 plus I. But then my second one would be x minus 2 plus I, which would go to x minus 2 minus I. I didn't do my conjugate correctly, so make sure you guys go back and fix that, please. Okay, so when I multiply this out, and I'm going to do all the work right now, And then I'm going to show you the shortcut. So if we were to, so don't do this, just watch. X squared minus 2x minus ix minus 2x plus 4 plus 2I plus ix minus 2I minus I squared. So things cancel out. 2x's would go to, it looks like negative 4x. So I would go to x squared minus 4x. My ix's go away. My 2i's go away. I squared, remember, is negative 1, so this really is the same as plus 1. So I'm going to add that to my 4, which gets me to 5. So that multiplies out to x squared plus 4x minus 5. So you can either do it the long way, or if you can see that we have a difference of squares here, with this being, let's say, my a, and this being my b, this being my a, and this being my b. And remember when you did difference of squares, you get a squared minus b squared when you multiply it out. So if I think of my x minus 2 being my a, I can square that, minus my I squared. So this foils out to x squared minus 4x plus 4, and that goes to our plus 1, right? So that gets you to your x squared plus 4x plus 5. So either way is going to get you there. So take it the long way, or if you can see the difference of squares, use the difference of squares. So now I'm going to multiply these guys together. So that gets me x squared plus 7x plus 12. And now I ran out of space. I wrote too big. So I'll move up here. So when we multiply all that out, I'll save ourselves the time and the energy, because I'm going to assume you can all correctly multiply that out. It's just a lot of work. And then combine your like terms. That's going to get you to f of x is equal to x to the 4th plus 3x to the 3rd minus 11x squared minus 13x plus 60. And there'll be your final answer. Okay, so don't make the mistake I did. Conjugate of 2 minus I is 2 plus I. That was a really silly mistake. I don't know why I did that, but I did. So don't you do it. All right, let's go to example 4. We have x equals 1 with a multiplicity of 2. So that means it's happening twice. So my linear factor for positive 1, 0 will be x minus 1. I'm just going to rewrite that twice. And now make sure I do my conjugate correctly. The conjugate of 1 minus I is 1 plus I. So we're going to do an x minus a 1 minus I and an x minus a 1 plus I. So that goes to x minus 1 plus I, x minus 1 minus I. So my difference of squares would be x minus 1 squared minus I squared. So x squared minus 2x plus 1 plus 1. So x squared minus 2x plus 2. And then my first 2 multiplies to x squared minus 2x plus 1. And then when we multiply all that together, we get g of x is equal to, I'm going to scrunch it in here, x to the 4th minus 4x to the 3rd plus 7x squared minus 6x plus 2. If you want practice multiplying that out, pause the video and multiply it out and see if you can get to those numbers. Okay. Example number 5, factoring a polynomial with complex zeros. So now we're actually going to start factoring it. So we have a 5th degree polynomial, and we want to factor it as far as we potentially can factor it to. So to be able to find 1, 0 is going to be our first move. So remember the rational root theorem from last lesson. We're going to find all of our options of p over q. So my p is 8, so 1, 2, 4, and 8. My q is 1, so that's nice. So I have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8 as my options. I'm going to cheat, and I'm going to pick one that I know works. So I'm going to go with 1. So we have 1, negative 3, negative 5, 5, making sure, do I have any holes? 3, 5, 4, 3, 2, 1, 0. No. 5, negative 6, and positive 8. All right, synthetic division, bring down the 1. 1 times 1 is 1. Adding is negative 2, negative 2, negative 7, negative 7, negative 2, negative 2, negative 8, negative 8, 0. Check. All right, so now we went from a 5th degree to a fourth degree. And we're going to keep on doing this until we get to a quadratic. Okay, so I'm going to pick another one of my zeros, and I'm going to cheat because I know which one does work. I'm going to go to -2. Oops, I should put my -2 up here. -2 should work. So bring down my 1, -2, -4, 8, 1, -2. Oops. Oh yeah, we're okay. -4, 8, 0. Check. So now we're down to a third. We need to do one more to get down to a quadratic. I'm going to go with 4. Bring down my 1, 4, 0, 0, 1, 4, 0. Check. So now I'm down to a quadratic. What is that finalized quadratic? Well, it's x squared plus 0x plus 1. I'm going to set that equal to 0. So how do we solve that? Well, it's not factorable. I'm going to solve this by using the square root property. I'm going to subtract that 1 over, which is -1. Square root. So let's go back to another sidebar. Remember, the square root of -1 is equal to I. So like the square root of -4 is equal to 2i. The square root of -7 would be I root 7. Remember all of that fanciness? So here, when we take the square root of -1, we end up getting x is equal to plus or minus. Remember, you always have plus or minus when you use the square root property of I. So now I have 1, 2, 3, 4, 5 zeros, which is what I need because I have a degree of 5. So now let's turn those into linear factors. All right, so our first one was x minus 1, so or a positive 1, so x minus 1. Then we went to -2, so that would go to x plus 2. Then we went to 4, so that would be an x minus 4. And then we have plus or minus I, so x minus I, x plus I would be my finalize. Yep, and then we factor it. Done. There it is. So we found all 5 zeros, both real and non-real, and we put it in factored form. So let's go back and just kind of remember Descartes' rule and put it into practice here. I have one change, so 1, it's like 2, 3, 4. So that means I would have at most 4, 2, or 0 positives. Well, in this case, we had what? 2 positives, right? And then if we do the negative version of that, that would be a -x to the 5th. That would say minus x to the 4th. That would go to plus 5x to the 3rd. That would say plus 5x squared. That would go to plus 6x. That would say plus 8. So how many sign changes do we have? Just 1, it looks like. So that means I would have 1 negative, which we do. So if I have 2 positives, 1 negative, then that means I would need to have 2 imaginaries. So just kind of putting Descartes' rule of signs into practice there so you can see it, which is kind of cool. All right, let's move on to example number 6. So it says the complex number z equals 2i is a 0 of the following polynomial. Find the remaining zeros and factor over the complex numbers. Okay, so we got our polynomial. So again, we're going to do the same thing. We're going to use our rational root theorem here to find all of our possibilities. So my -60. So p is -60, q is 2. So 1 and 60, 2 and 30, 3 and 20, 4 and 15, 5 and 12, 6 and 10, all over 2, so 1 and 2. So I have a 1, I've got a 1/2, I've got 1, and I got 2 over 1, so 2 over 2 is already taken. Then a 3 over 1, so plus or minus 3, plus or minus 3/2, plus or minus 4. 4 over 2 already taken care of. 5 over 2. 6 over 2 already have covered. 10 over 2 is already covered. 12 12 over 2 is already covered. 15 over 2, 20. All right, oh my goodness. 20 over 2 is already covered. 30 over 2 is already covered. And 60, I guess, is the last one. Oh boy, that's a lot of possibilities. Yee. So maybe we don't want to have to rely on guessing and getting lucky. So maybe we should try to come up with a different option. I mean, I guess we could try to get lucky. You think you could try to get lucky each time? Well, let's just come up with a different option. Maybe you like getting lucky and just go with it, then go with it. But I'm going to show you another option that we could potentially use. So let's go to that complex number of z equaling 2i. So 2i, we know, would have a linear factor of x minus 2i. And then the conjugate would be x plus 2i, right? And when we multiply that out, we're going to get x squared minus 4i squared, which is really x squared plus 4. So I already know that those have to be factors of the polynomial. So what if I make that a divisor of my dividend and do some long division with that? Because we can't do synthetic division, because I can only use synthetic division when I'm doing linear divisors. So let's do some long division. Let's see how this works. So 2x to the fourth plus x to the third minus 7x squared plus 4x minus 60. So when I take x squared into 2x to the fourth, or divide 2x to the fourth by x squared, we end up getting 2x squared. And I'm going to put that over top of my x squared term in the dividends. Now I get we get 2x to the fourth, and then 2x squared times 4 is going to get me 8x squared. I'm going to put that underneath the x squared. So when I subtract, I end up with x to the third minus 0x to the third. So that's just going to be x to the third. And then negative 7 minus 8 is going to get me negative 15x squared. And then I'm going to bring down my next term, which is a 4x. So now x squared goes into x to the third one time x, right? Or divided out gets me an x. So then I have x to the third plus 4x. Well, 4x, so leaving a gap, plus 4x. So when I subtract, I end up with negative 15x squared. That goes to 0. Bring down your negative 60. So that's going to just be a negative 15. So negative 15x squared plus 60. So that's nice. I should get a remainder of 0, right? Because we knew that it was a divisor into our original polynomial. So now what am I left with? Aren't I left with a quadratic? And wasn't that our goal of synthetic division prior? Was to try to keep dividing out until we get to a quadratic? Yeah. So instead of trying to guess, so we started with a fourth degree, I had to maybe guess 2 correct zeros, and maybe you would be able to do that, and you'd be fine doing that. If you want to go with it, go with it. But this is another method that we can use if you're given an imaginary 0. So now let's go ahead and look at that finalized quadratic of 2x squared plus x minus 15 is equal to 0. So that 2 times negative 15 is negative 30. Factors of negative 30 that get you to 1 would be 6 and negative 5. Put them both over your leading coefficient of 2. Reduce fractions if you can. So x gets attached to the denominator. So I get x plus 3. 2x minus 5 is equal to 0, which gets me zeros of negative 3 and 5 halves. All right, so what we're trying to do, find the remaining zeros and then factor it completely. So my zeros are the original 2i, negative 2i, negative 3, and 5 halves. So the factors would be x minus 2i, x plus 2i, x plus 3, and 2x, I'm running out of space, 2x plus 5, or minus 5, minus 5, minus 5. Sure, it's minus 5. Okay, so just another option that you can work with if you don't want to work through all of those using your rational root theorem. All right, example 7, right? The following polynomial is a product of linear and irreducible quadratic factors, each with real coefficients that is to factor over real numbers. Okay, so we're at a cubic. That means we probably should try to do a synthetic division once to get to a quadratic. So what are my options? So P over Q. So we're at 2 and 1 over 3, so 1 and 3. So all my options are 1, 1/3, 2, and 2/3. Okay, I'm going to try 1 out. So do I have any holes? Cubic, quadratic, linear, and constant? No. I have no holes, so I don't need a 0. Bring down your 3. 3 times 1 is 3. Adding is 1. 1, adding, multiply 0. Check. That was good. So that goes to 3x squared plus 1x plus 2. Okay, so it wants us to write it as a product of linear and irreducible quadratic factors with real coefficients. So that is a factor over real numbers. So things that we need to think about is, 1, is this factorable? So if I take 3 times 2 and that gets me to 6, are there any factors of 6 that would get me to 1? Well, my only factors of 6 are 1 and 6 and 3 and 2. When I add those together, I get 7 and I get 5. Neither of them make 1. So it is not factorable. So because it's not factorable, and I want to write my answer as a product of irreducible quadratic factors with real coefficients, my factors would just stay as such. So we have my first 0 we said was a 1, so that would be a linear factor of x minus 1. And then I would just put that final result of 3x squared plus x plus 2 in my answer, right? Okay, so think about it this way. So think about possible answer forms. Answer forms. So we could potentially have like x plus a, x plus b, x minus c, or whatever it would be. Or it could be something like x minus a, in this case it was a minus, and then it's times some type of quadratic that's not factorable. Okay. I mean, could we solve that? Yeah, we could solve that using quadratic formula probably would be best instead of completing the square, right? So if we did quick quadratic formula, that'd be a good quick review. So x equals negative b plus or minus b squared minus 4ac all over 2a. So that would be what? 12, 24, 1 minus 24, so it'd be root negative 23, negative 1, plus or minus 6. So I would go to negative 1 plus or minus I root 23 all over 6. So my zeros would be negative 1 plus I root 23 over 6 and negative 1 minus I root 23 over 6. Well, that would look pretty ugly if you were trying to write that as linear factors, right? So let's not even do it. So let's just leave it as that non-factorable form. All right, last page. Sketching a graph with repeating zeros. So now we're going to get into sketching a graph, the polynomial function with the given zeros, multiplicities, and given sign, and sign of leading coefficients. So we have a 0 of negative 3 with a multiplicity of 2. So that would look something like x plus 3 squared. And then we have a 0 of 4, so x minus 4 with a multiplicity of 3. And it's telling us that our a is positive. So my degree, right? My degree of this whole entire thing is 5, because I'm just adding my exponents together, which is odd. So remember, odd graphs usually do this. And since it's positive, that's how my behavior is still going to stay. At x plus 3, since I have a degree of 2, that means it's going to just touch at the graph. At x minus 4, it's going to cross because it has a degree of 3. Okay, and then let's mark those out. So negative 3, we're going to have something happening there. and 4. We're going to have something happening there. I'm going to sneeze. Okay. All right, so now let's get some values. So what happens when we plug in 0 into the whole entire function? Well, then I get 3 squared times negative 4 to the third, which is negative 576. Ooh, boy. My end behavior, so the limit as x approaches negative infinity of our function is going to be going to negative infinity. And the limit as x approaches positive infinity of our function, which I guess our function is, we don't have a name for it, so we'll stick with f of x, is going to be equal to positive infinity. So, I don't know, I'm just going to put 0 because that's very large. So 0, negative 576. Let's put down here. So we have negative end behavior. We're going to come back down, and then we're going to cross. So we're going to have some type of like point of inflection happening here because it is cubic, right? So now I'm going to label for 0 and negative 3, 0, and make sure I have arrows on either end. I guess I could have made this curve a little bit better. There we go. Maybe that's a little bit closer to what it would be. All right, let's go ahead and do the last one. So we have a 0 at negative 1 with a multiplicity of 2. So x plus 1 squared, x minus 3 for the 3, and multiplicity of 2. So my degree is 4. So that means we're going to have our behavior either being up and up or down and down. Since my a is positive, it's going to be down and down, right? So the limit as x approaches negative infinity of f of x is going to be negative infinity. The limit as x approaches x of f of x is going to be also negative infinity. Now let's see, we got what's happening here. We're going to have a touch and a touch at both. So at negative 1, our graph's going to touch. At 3, our graph's going to touch. Let's find that y-intercept. So plugging in 0 will get me 1 squared times negative 3 squared. So negative 9, right? Oh, nope, it's not going to be negative 9 because my leading coefficient has to be negative. So this multiplies to get to 9, but I need my leading coefficient to be negative, which would then result to make that probably a negative. All right, so then what do we got? We got 0, negative 9, I'm going to put down here. All right, so my end behavior is going to go down this way. My end behavior is going to go down this way. So now he's got to figure out what's happening in between. I got my y-intercept here, and then maybe it's doing something like that. Sure, looks good. All right, and that should conclude your notes.